All right, one last video I want to make before I go to bed tonight. This is the homework for 5.1 where you're estimating areas with rectangles. And I think there's nothing too tricky in here. I think the questions are more or less straightforward. The notation might be slightly different, so maybe I can talk you through that. This first question says approximate the area under the curve y equals x squared from x equals 2 to x equals 4 using a right endpoint approximation with 4 subdivisions. What that means is calculate R4. R because right, 4 because 4 subdivisions. So calculate R4. Your curve is y equals x squared. A is 2, and B is 4. So maybe you can calculate delta x, you can calculate the different xi values, you can calculate the area of all the rectangles, and then you can come up with your answer over here. I think the values will work out fairly nicely if you deal with fractions instead of decimals, but you can do whatever you want in this one. Same idea in number 2. There's really no difference here except now it's a left sum with 6 subdivisions. So you're calculating L6. It'll take you a little while. Sorry, 6 subdivisions is kind of annoying. But we're going from x equals 0 to x equals 3. So again, 6 subdivisions will work out pretty nicely when A and B are 3 apart. Note that your curve now is x squared plus 4. So that's questions 1 and 2. Question 3, kind of the same idea. Now we're dealing with y equals x cubed. Be careful, we've done so much stuff with x squared, both in the examples and in these first 2 problems. It'd be really easy to figure out all your xi's and then just, all right, this is getting tedious, I'm bored, I have something on in the background, I'm not paying attention, and square all those xi values instead of cubing them and go through all the work and get the wrong answer. I don't want you to do that. I know these problems get a little bit frustrating. Make sure you're cubing them here. Question 4, this one will probably take you the longest because the function is kind of annoying, 3x squared plus 12x plus 5. So when you plug in xi, you'll be plugging it in 2 different spots in the function to figure out the heights of the different rectangles. And the interval goes from 0 to 7, so that's written a little bit differently. That's just saying a is 0 and b is 7. And we're using 4 approximating rectangles and right endpoints. So R4 with a equals 0 and b equals 7. Oh, that's going to be annoying, right? Delta x is going to be 7/4, I think. This will be kind of an annoying problem just numerically to work out. Problem 5 is kind of more of the same. Now the a is -2 and the b is 1, and we have 8 approximating rectangles. God, that's going to be annoying. I think I'm going to get rid of one of these problems for you. 5 is the last one that's required, and then 6 was the extra credit one. And this felt like about the right length to have 5 of these. But really, this one is a double and this one is a double. And I think if you actually work through all these with the formulas, by the time you're done, you're going to wish there were less problems. Right? I don't want to make your homework too short because I want to make sure everyone understands these. But I also don't want to just waste your time. I know you got other stuff going on. It's hard to be a teacher. Like, I really want to make these long enough so you get enough practice. What I'm going to do is I'm going to delete one of these. Which one is worse? 8 rectangles? Yeah, that one's gone. I'm going to get rid of this question 5. So your homework will only have 5 questions on it. This one will be gone. And the 5th one will be the extra credit one. And hopefully that's enough for you to get the practice on what you need. And if you need more practice, remember you can always refer back to your book. Right? You have a book, a regular textbook here. It has tons of different examples that you can look through for the different sections. You can just work a couple of their examples if you feel like you need extra practice on this. At any rate, I'm going to get rid of this question with 8 approximating rectangles where you got to do R8 and L8. But I'll keep this one where you have to figure out both R4 and L4. So question 4 will be kind of a double question in a sense. And then question 6, the extra credit one. This is the first application of this stuff. I haven't ever explained why you might want to find the area underneath the curve. One reason you might want to find the area underneath the curve is because if you have a function that tells you speed, right? So here's my speed, my velocity. And the x-axis here is time. Then the area underneath the curve between 2 different times, time 1 maybe and time 2, is the exact same as the amount of distance that you would travel between these 2 time periods. And you're like, whoa, weird, why does that work? Well, it's not as surprising as you might think because distance is just rate times time, right? Maybe you saw this formula way back in a high school math class or something. Because distance is rate times time, it kind of makes sense that if my rate were constant, right? If I'm going 30 miles per hour from time 0 up to time 3, right? 30 miles per hour for 3 hours, then I'm going to travel 90 miles, right? Oh, that's exactly the same as this area. 3 times 30 is exactly 90. So it kind of makes sense when your speed is constant that if you're going a constant 30 miles per hour for 3 hours, you travel 90 miles. It also works when your speed changes. It's just a little bit harder to figure out how far you've traveled. Okay, why am I going through all that? Because in this, you're supposed to estimate the distance traveled. And they tell you the time and they tell you the speed. Okay, I think the hardest part is just understanding what you're supposed to do. What you're supposed to do here is the exact same as what you did in all of these problems. It's the exact same. It's actually even a little bit easier because now you don't have to plug these x values. I know it says t, but these are your x values. The time goes on the x-axis. Now you don't have to plug those into a function. This is telling you what would come out of the function. So this is telling you that the height of the graph when the x value equals 0 is 28. The height of the graph when the x value equals 6 is 37. The height of the graph when the x value equals 30 is 19. It's giving you all that information. It's telling you the f of xi values. So if you have all of these, maybe you can estimate the distance traveled. Estimate the distance traveled by the vehicle during this 30-second time period using the velocities at the beginning of the time intervals. So for my first rectangle, which goes from 0 to 6, I want to use this height. For my next rectangle, which goes from 6 to 12, I want to use this height, and so on. If I use the beginning of the time intervals, I'll be interested in some of these values, but then I could do it again using the velocities at the end of the time intervals. It's just a matter of whether my rectangles look like this or whether my rectangles look like this. Anyways, that's the extra credit question. If you get anything out of that, great. We'll do a lot more with applications later on. I feel like at this point in the class, we're just kind of learning the basics. We're not trying to worry about where this might be applicable. But I was looking for an extra credit problem, and this is one that popped up in the library that I choose from, so I figured it was good enough.